This is a video on simplifying radicals. To simplify radicals, we must first check to see if our radicand is a perfect power. And since that's our first step, the first thing I want to look at is just a review of perfect squares and perfect cubes and talking about perfect powers. So for the perfect squares, 1's a perfect square, 4, 9, 16, 25, 36. Basically any number that you can multiply by itself that gives you a number is a perfect square. So 1 is a perfect square because it's 1 times 1, or 1 squared. Right? 4 is a perfect square because it's 2 to the second power, or 2 times 2. 9 is a perfect square because it's 3 to the second power, right? 3 squared. 16 is a perfect square because it's 4 squared, and so on. We can keep going like that. For perfect cubes, they result from a number times itself 3 times, resulting in that number. So for 1's a perfect cube because it's 1 to the third power. Then 8's a perfect cube because that's 2 to the third power. 27's a perfect cube because it's 3 to the third power. 64 is a perfect cube because it's 4 to the third power. And I could continue like this, right? So 4 times itself 3 times gives you 64. This also applies for variables, but in a different type of way. Perfect squares for variables have even exponents. In other words, we have x squared, x to the fourth, x to the sixth, x to the eighth. And we could go on like this pretty much forever. For x squared, really we know that that's going to be x to the second power. For x to the fourth, we know that's x squared squared, right? So when you have an exponent, you're raising it to a power, you multiply. So 2 times 2 gives you 4. So that's how you know x to the fourth is a perfect square. X to the sixth is the same as x to the third to the second power, right? 3 times 2 gives you 6. X to the eighth is the same as x to the fourth to the second power. We can continue like this. So for a perfect square, the variable has an even exponent, or an exponent divisible by 2. For a perfect cube for variables, they have powers that are divisible by 3, mainly because x to the third here is x to the third power. X times itself 3 times. X to the sixth is really x squared raised to the third power. X to the ninth is really x to the third raised to the third power. X to the 12th is really x to the fourth raised to the third power. So you could write these all as some base raised to the third power. Realize for a perfect cube, all the exponents are divisible by 3. Alright, so that's how you know something's a perfect cube if it's a variable. So, given a radical or a root of a specific index, the easiest way to determine if the radicand is a perfect power of the index is to divide the exponent by the index of the root. Basically what this is saying is that if I have a root, all I have to do is divide by the exponent, or divide the exponent by the root, and I can evaluate if it's a perfect power or not. Here's some examples. So for the first one here, we got the 7th root of x to the 21st power. Well, if I look at x to the 21st, alright, so that's the power, and I divide by 7, right, that's the root, I get x to the third power. Since that result divided evenly, I know that this is a perfect, alright, so x to the 21st is a perfect 7th power. Right, because I could divide 21 by 7 and it divided evenly to give me x to the third. Similarly down here, right, I got the cube root of x to the 12th. So I really want to look at this as x to the 12 divided by 3 power, and 12 divides by 3 evenly, so we get x to the 4th. Alright, and that tells us that x to the 12th is a perfect cube root, or you could say third root, right, those are used interchangeably. And down here I've got the square root of x to the 18th. Remember, if you don't see an exponent, or you don't see an index on the root, realize that's the square root. So this is really x to the 18 divided by 2, which equals x to the 9th power. So then we can say x to the 18th is a perfect square root. Right, or you could say, second root instead of square. So all these were perfect powers, alright, meaning that they all divided evenly by the index. Alright, notice all these are perfect powers, so when we divided by the index, they all came out evenly. And this way that removed the radical symbol. Alright, so when you have a perfect power, when you simplify it, the radical symbol is gone. Now don't forget that for numbers it still works the same way that it always has for radicals, meaning what number times itself that many times gave you what's inside. So for part A here, if we want to simplify, the cube root of 64, it means what number times itself 3 times gives me 64? Well, the answer here would be 4. The reasoning is because 4 raised to the third power equals 64, right? 4 times 4 times 4 equals 64. So the answer here is 4. Part B, the fourth root of 16. If I'm looking for the fourth root of 16, I'm saying what number multiplied times itself 4 times gives me 16? Well, the answer here would be 2. Because 2 to the fourth power equals 16. Right? 2 times 2 times 2 times another 2 gives us 16. And for this last one down here, the square root of 81. Remember, this square root means that we're really saying what number times itself gives you 81. Well, that answer is 9. And that's because 9 squared equals 81. Remember, if you don't see an index on here, you really should think of it as a 2. So don't forget that for numbers you still do the same thing. There is no dividing like we just did for the exponents on variables. So what if a radical isn't that of a perfect power? Alright, so what if we don't have a perfect power on the inside? And basically we use this product rule for radicals to help us navigate that. So it says for non-negative numbers a and b, if I have the nth root of a times b, so I have two things multiplied together inside of a radical, inside of a root, you're really allowed to take the root of each one individually. So I'm taking the root of a and then multiply by the root of b. This will help us actually when we try to break down non-perfect power, because we can actually create a radical that has all the perfect powers in it and then a radical that has all the non-perfect powers in it. Alright, so let's take a look. So to simplify, the square root of 28. Alright, square root of 28 doesn't evaluate nicely because we don't have an integer times itself that gives us 28. So since we don't have that, we really want to break up square root of 28 into two square roots. Alright, and in the first square root I'm going to put anything that's perfect. Alright, in this case we're looking for a perfect square. Alright, in the second one I'm going to put anything that's non-perfect. Alright, so when I look at the square root of 28, I want the highest perfect square that's a factor of 28. So I'm thinking of numbers that multiply to 28. And the highest perfect square that's a factor of 28 is 4. Because 4 times 7 gives me 28. So 4 is a perfect square, so putting that in the first one. 7 is a non-perfect factor, so I'm just putting that in the second one. And now you can evaluate this. The first one, the square root of 4, breaks down to 2. And notice we don't write the radical symbol anymore because we took the square root of 4. So that's 2, and then the square root of 7 stays square root of 7. So your answer here is 2 square root of 7. Because square root of 7 doesn't break down evenly and you can't break it down any further. Alright, so you always want to break down your radicals into the perfect values going first, the perfect powers going first, and the non-perfect values going second. So for the next one we want the cube root of 54. So for 54, it's not a perfect cube. Right, so there isn't a number times itself 3 times, it gives you 54. So we know we're going to try to break this up into two cube roots. In the first one I'm going to put the perfect cube factors because it's the third root, so we need the perfect cube factors of 54. And in the second one I'm going to put the non-perfect factors. Right, or the non-perfect cube factors, maybe I should say. Alright, if I'm looking for the perfect cube factors of 54, alright, you want the highest factor of 54 that's a perfect cube. Alright, and that would be 27, because 27 is a perfect cube, because 3 times 3 times 3 gives you 27. So 27 is perfect cube, so that's a factor of 54, and it's perfect cube, so we want 27 times 2. And then if you take the cube root of 27, well, that's going to be 3. Because 3 times itself 3 times gives you 27, and then this will be the cube root of 2. You can't evaluate that. There's no number times itself 3 times that gives you 2, and so you got it. Alright, you could also apply this to variables. So if I got the fourth root of x to the 23rd power, remember how you can tell if this is a perfect power. If you can divide this by the index, right? So if I could divide the power on x by the index, then it's a perfect power and I can just evaluate it right away. If not, I have to make two radicals. So x to the 23rd, 23 is not divisible by 4. So I know it's not a perfect power, so right away I know I'm going to need two radicals, each being the fourth root because this was the fourth root. And we want x to the 23rd to be divisible by 4. So we want the highest power closest to 23 it's divisible by 4, which is x to the 20th power. Alright, so the highest power close to 23 without going over it's divisible by 4 is 20. And this, whatever's left over, would go over into the next set. So this is our perfect piece, because 20 is divisible by 4. And our non-perfect piece here, which would be x to the third power. Remember, the total in the power is 20 plus 3 should add to 23, whatever you had here. And now you want to evaluate each of these. Evaluating, right, just so you write this down, it's a non-perfect piece in the second one. So evaluating each of these, we've got the fourth root of x to the 20th. This is really x to the 20 divided by 4, so this is going to be x to the 5, right? Because you're doing 20 divided by 4 here. Times, now here, this is the fourth root of x to the third. Well, 3 isn't divisible by 4, and you can't pick any number closest to 3 that divides by 4. That one doesn't break down any further. So this is the fourth root of x to the third, and that would be your answer. Alright, make sure that when you pick the first perfect square, it's the closest, or the perfect factor, it's the closest number that's divisible by 4 to 23. If you chose a smaller number, then it wouldn't break down properly, it wouldn't be simplified completely. For the next one, we get the cube root of y to the 14th. Now remember, you should check to see, is 14 divisible by 3? In this case, 14 isn't divisible by 3, so we know we're going to have to make two roots. Alright, so we're in two cubed roots here. And the first cubed root, remember, we're going to put our perfect pieces, our perfect factors. And in the second one, we're going to put the non-perfect factors. And for this first one, we want the closest number to 14 that's divisible by 3 without going over. So we want y to the 12th power. And for the second one, we just want to make sure they add to 14. So if I use 12 here and I need 14 total, there should be y to the second power here. We break down the first one. So the cubed root of y to the 12th is y to the 4th, because you do 12 divided by 3 gives you y to the 4. And the second one shouldn't break down, right? We got y to the second power divided by 3. Well, that doesn't break down, so this is the cubed root of y squared. Alright, and for the next one, we got the square root of z to the 37th power. Remember, the index on this is really 2, even though you don't see it for square root. 37 isn't divisible by 2, right? It doesn't divide evenly. So we want to set up two square roots, alright? And this is square root because we didn't see a number here, so these are each square roots. So I want the closest number to 37 without going over, that's divisible by 2, which would be z to the 36. And then however many are left over, well, there's 37 total, 36, and this should be z to the first. And then evaluating this, the square root of z to the 36, remember how this works. For an exponent, you divide by the index. So you're dividing by 2 here. 36 divided by 2 makes a z to the 18th. The common mistake people make is to put 6 because they take the square root of 36. But remember, that only applies to if you have an integer. Alright, if it's an exponent, you divide by the index. So 36 divided by 2 gives you 18. And this square root of z just stays square root of z. Alright, so basically here's your steps to simplify radicals. We've already done most of this. Your first step, you want to determine if your radicand is a perfect power of the index. Alright, if so, you want to simplify the radicand. And that was the very first thing we did. We had things that were perfect powers, we just divide the index, and then we're done. If it's not a perfect power, then we move on to step 2. Alright, so step 2 says to rewrite the radical, alright, as a product of radicals. And that's what we were just doing a second ago. So if you don't have a perfect power, you want to write it as a product of two radicals. In the first radical, you want to have anything that's a perfect power in there. And in the second radical, you want to have all the remaining factors. So you're breaking it down based on its factors. Alright, the perfect power factors go in the first one, the non-perfect power factors go in the second one. And then step 3, you want to simplify the first radical, just like we did in the last step, and then you want to leave the second radical as is. So let's take a look at a few more examples. So if we wanted to simplify the square root of 16x to the 8th y to the 20th. First we should determine if this is a perfect power or not. Alright, so we want the square root. Alright, so everything inside of here has to be a perfect square in order for it to be a perfect power. Alright, if it's not a perfect square in here, then we have to write two radicals. If everything in here is a perfect square, then we just evaluate it. So 16, alright, this coefficient is a perfect square because 4 times 4 gives you 16. X to the 8th is a perfect square power because 8 is divisible by 2. Alright, and y to the 20th, alright, is also a perfect square because 20 is divisible by 2. So I can break this one down right away. These are all perfect squares. So square root of 16 is 4. Square root of x to the 8th is x to the 4th power because you're doing 8 divided by the index, which is 2, don't forget. And then y to the 20th divided by 2 makes this y to the 10th power. No radical symbol because you already evaluated it. For part B, we need to look to see if everything inside is a perfect cube. Remember, for coefficients, right, for the 64 in front, we need to know, is there a number times itself 3 times that gives me 64? And the answer is yes, because that'll be 4 times itself 3 times will give me 64. For the variables, you have to look at the exponents. Alright, so the exponents here, we got 6 and 21. They have to both be divisible by 3 to make this a perfect cube. Well, 6 is divisible by 3, and so is 21, so we know it's a perfect cube. We can evaluate it right away. Alright, it's a perfect power. So 64, we said the cube root of 64 was 4. Cube root of x to the 6 is x to the 6 divided by 2 power, which is x, or 6 divided by 3 power, which is 2. And y to the 21st, taking the cube root of that, is y to the 21 divided by 3, which is y to the 7. So we got 4x squared y to the 7. And for this next one, alright, you want to check to see if we're taking the cube root of x to the 11th, y to the 14th, if everything on the inside is a perfect cube. There's no coefficient, so we don't have to worry about that. For variables, remember the power has to be divisible by the index. Well, is 11 divisible by 3? The answer would be no, because 11 doesn't divide by 3 evenly. So right away, as long as one piece doesn't work, that means the whole thing has to be written as two separate radicals. So I need the cubed root and the cubed root. Remember, my first one is going to have all the perfect powers. The second one is going to have all the non-perfect factors. So I have x to the 11th. I want the closest number divisible by 3 to 11, and that would be x to the 9th. And then however many left over go in the second one, the non-perfect piece, which would be x to the 2nd, right? Because if there's 11 total and we put 9 here, there has to be 2 left over. The y to the 14th, is that a perfect cube? Well, 14 doesn't divide by 3 evenly, so we need y to the closest power to 14 divisible by 3 is y to the 12. And then whatever's left over will go in the second set, which would be y to the, if this is 14, and we use 12 of them, we need 2 more, so we got y to the 2nd. We can evaluate the first radical. The second one's going to stay the same. So the cube root of x to the 9th is really x to the 3rd power, because you do 9 divided by 3, which gives you 3. And then the cube root of y to the 12th is y to the 4th power, because you're doing 12 divided by 3, which gives you 4. And then the cube root just stays. So this will be x squared, y squared, and that's it. You can't break that down any further. Alright, let's take a look at a few more. Alright, so let's take a look at the next one. We get the square root of 18x to the 4th, y to the 7th. Now, this is a square root, so we need to check to see if everything inside is a perfect square. And in this case, it isn't. Right away, you can see 18 is not a perfect square, so you know you're going to need 2 radicals. Alright, and these are square roots, so we don't have to put an index on them. And we want to say, what's the highest perfect square factor of 18? And the highest perfect square factor of 18 is 9. Alright, so 9 times 2 gives me 18, so we're going to split up as 9 times 2. X to the 4th, alright, is already a perfect square because 4 is divisible by 2, so I'm going to put x to the 4th right in the first one. I'm not going to evaluate it yet. I'm just placing things, alright, so I'm just sorting factors. And y to the 7th, that's not a perfect square because 7 is not divisible by 2, so we're going to need y to the closest power to 7 that's even, without going over, would be y to the 6th, and then we need one more y here to make that total y to the 7th. And then we can evaluate each of these. The first one's all perfect squares, remember, so we can evaluate everything inside. Square root of 9 is 3. Square root of x to the 4th is x to the 2nd power because you're dividing the exponent. 4 divided by 2, which gives you x to the 2. And then y to the 6th, 6 divided by 2 gives you y to the 3rd power. So we got 3x squared y to the 3rd, and the second radical just stays the square root of 2y. That's the non-perfect one. So it would be our answer. For this next one, notice we got 32x to the 13th, y to the 5th, raised to the 1/4 power, right? So 1/4 is the exponent. That really means to take the 4th root of it. So let's actually write that as a 4th root. This is the 4th root of 32x x to the 13th, y to the 5th. And now we got to check to see if these are perfect fourth powers inside. 32 isn't a perfect fourth power because there is no number times itself 4 times. That gives you 32. So right away we know this isn't a perfect fourth power. We can split this up. 2 radicals. First one will contain perfect pieces. The second one will contain non-perfect factors. So 32, the highest perfect fourth power of 32 is actually 16. Because 16 is the same as 2 to the fourth power. And then 16 times what gave me 32? Well, 16 times 2 did. So 2 is the non-perfect piece that's going over here. X to the 13th, we need x to the closest power to 13 that's divisible by 4 without going over. So that'd be x to the 12. Then we need a single x over in this one. And then for y to the 5th, we need y to the closest power to 5 without going over. That's divisible by 4 is y to the 4. And we need a single y here. We can evaluate the first one, remember. So the 4th root of 16 is what number times itself 4 times gives you 16. So the answer there is 2. X to the 12th, 12 divided by 4 gives us x to the 3. And y to the 4th divided by 4 is y to the 1, which we'll just write as y. And then the second part stays the same, the 4th root of 2xy. And we'll do this one here last. So we got 8x to the 4th, y to the 7th raised to the 2/3 power. Remember what this means. The number on the bottom means the root, so we know we're going to take the cubed root. The number on the top means the power. It means what to raise it to. So I'm going to really have 8x to the 4th, y to the 7th raised to the 2nd power. And then I'm going to take care of raising that part on the inside of the 2nd power first before I deal with the root. So this will be the cubed root of, now remember you square each piece inside, so 8 squared is 64. X to the 4th squared, remember when you raise an exponent to a power you multiply, so this is x to the 8th. And y to the 7th squared, remember power to power you multiply is y to the 14th. Now from there you're going to do what we normally would do, which means first we should see if this is a perfect cube power. Well, 64 is a perfect cube because it's 4 to the 3rd power. X to the 8th though isn't a perfect cube because the exponent isn't divisible by 3. So right away we need 2 radicals. In the first one we're going to put all the perfect pieces. So 64 we said, okay, that's already a perfect cube root, so I'm just going to write it as 64. Notice I'm not evaluating it yet. And then I've got x to the 8th here, which we said isn't a perfect cube, but you know we can get the closest power to 8 divisible by 3, which would be x to the 6th. We need an x squared over here. Notice when I put 64 in here, I didn't have to put anything over on this side as well, because there is no coefficient that needs to be here. And then y to the 14th, we need y to the closest power to 14 divisible by 3 is y to the 12th. And then this will be y squared, because we need 14 total. We can evaluate the first one. Can't do anything with the second. Cube root of 64 is 4. Alright, cube root of x to the 6, remember we're doing 6 divided by 3, so it'll be x squared. And then y to the 12th, remember taking the cube root of that, you're dividing by 3 is y to the 4th power. And then we have left over here just the cube root of x squared, y squared. Alright, maybe we can make that look a little nicer there. So we got 4x squared y to the 4th times the cube root of x squared, y squared. Alright, here's a couple for you to try on your own.